Topics for today, 22, which we just started last time, this idea of the divergence theorem. And then we'll spend maybe the last half hour going back and picking up 13.4, which is about cross products. So homework help 3 to 4 today and tomorrow. And I'll probably actually need to leave a couple minutes before 4, because I have a meeting that starts at 4 that I need to get ready for. Friday we'll do 20.3, and then homework help 3:30 to 4:30, and I have more flexibility on Friday afternoon. And then, sorry, go ahead.
I think Friday I have homework help 6:30 to 7:30, and Corey.
And Ian to 7:30. Okay, great. And then next week, which is also week 10, we'll do 24, 25. That's the last chapter in the book. And then we'll do a summary on Friday. And I'd wanted to do some electricity and magnetism, some physics, but I think I'm going to wait until after we're through 23 and 24. So I'll sort of save that for either Wednesday or Friday as part of the summary. OK. So last time, the main topic was this notion of divergence. And so here's sort of a summary of what we did last time. And I just wanted to remind you of this. And then I'm going to sort of restate the divergence theorem slightly differently. So we started by introducing this idea of flux density. And I did it in analogy with mass density, where the mass varies through space. And so at a particular point, you figure out the flux out of a closed surface centered on that point. You divide that by the volume of the surface. You take the limit as that gets smaller and smaller. That's what this looks like in symbols. And that's the flux density. So that's a geometric, or maybe almost a physical interpretation of what flux density is. And then I also argued. I did a little more than assert, but I didn't quite prove. I suggested, a little more than hinting. Anyway, I stated that the flux density algebraically can be written like this. And then notation, we sometimes call this div f, or I like del dot f, because it makes it clear that it's a scalar derivative. So del dot f is a scalar derivative of a vector field. So the last part of the course, we're doing calculus on vector fields. And we've learned about some ways of integrating them. And in chapter 20, we're learning about some ways of differentiating vector fields. My phone used to automatically shut off during classes, but it seems to have forgotten to do that. OK, so this is I think more or less where we got to last time. So now suppose we wanted to know. Set this up. Suppose we want to know over some closed surface. So this could be this could be a potato, who knows what it is. But we want to know some flux out of some surface. The point is, it doesn't have to be a rectangle or a sphere. It could be some kind of strange thing. So this is flux out of the entire surface. And I claim I could write this as flux out of many small surfaces. And here's a picture for that. So we could just walk around the surface and see how many butterflies are flowing out at every point in the surface. Or we could do something much less efficient. We could, it shouldn't be that hard to draw cubes, but apparently I can't talk. OK, there we go. So we could imagine taking two small cubes, and we could calculate the flux out of this one and the flux out of this one. And I claim that that's the same as the flux out of this one. So maybe an analogy isn't needed, but that usually doesn't stop me from analogies. So suppose we wanted, so like maybe these could be countries. This could be like the Netherlands, and this could be Belgium. And we might want to know, like, what's the net trade of chocolates, net chocolate flux out of Belgium and the Netherlands. And so we could just like stand, and those are countries that, if I have my geography right, share a border. So I think, sure, they do now. So anyway, so you could just look at the outside of those two countries, or you could say, what's the net flux of chocolates in the Netherlands? What's the net flux of chocolate in Belgium? And there's going to be some, presumably, Dutch-Belgian exchange of chocolates. But what one country would experience as a positive flow would be negative to the other, and it's the same border, so they're going to cancel out. So the net flux, the net chocolate flow of this country plus this country is the same as the net chocolate flow of those countries put together. And so you can probably see where this is headed. Let's imagine these were tiny little countries, provinces, towns, and so on. And so we could take this entire big surface and express it as a sum of the flux out of many small surfaces. And why might we want to do that? Well, we know how to think about the flux out of many small surfaces, because that's the divergence. I guess I'll write it this way. Divergence is flux density. Flux density times volume gives you flux, just like density times volume gives you mass. And now you can probably see where this is headed. Hey, we're summing up a whole bunch of small delta v's. Aha, that's a volume integral. V del dot f dv. So let me just write this one more time. So f dot dA, sum of the volume of the divergence, dv. V is enclosed. Sometimes that's written this way, by S. So this has to be a closed surface, and the volume V here is the volume of the volume enclosed by S. And F must be continuous on V. And this is a divergence theorem. So I'd mentioned that last time, but I just wanted to use a slightly different argument to get here. All right. So let me say 5 to 10 minutes more of things about this, and then we'll start putting this to use for us. So the first thing I want to say is that this is another form of the fundamental theorem of calculus. So we've seen before, and so that takes a statement about what's happening along an interval from t equals a to t equals b, and turns it into a statement about what's happening only on the boundary of that interval, which is just 2 points. We've seen the version of this for gradients. So now it's still a line or a curve, but it's a curve that's not necessarily a straight line. It's on an interval. But if we have the line integral of a gradient, so this is an integral of some type of derivative, an integral of some type of a derivative, converts that to a statement about what's going on the endpoints or the boundary. we've seen Green's theorem. And so the curl here, this is, I should have written this the other way around. This is an integral over a region, the surface S, and we convert it into a just SC. So we're taking a statement about an area integral, and because it's a type of derivative, that turns into an integral that's just around the boundary of the surface. And here we have a volume integral that, because it's a type of derivative, gets converted to a surface integral. So these fundamental theorems take an integral and replace it with something that's just going on in the boundary of the region. And that region could be 2D and turns a 2D thing into 1D. The region could be 1D and it turns it into 0D, just 2 points. Or it could be 3D and it turns it into 2D. So that's kind of neat. And we'll see a variant of this next time. All right, that was one thing I want to say. What else do I want to say? So let's just think about units on this for a second. So imagine this was a velocity field. So let's just think, so like units. If F was meter per second, that's sort of like the simplest sort of field to think about, then this is going to be meters per second times an area. That's going to be meters cubed per second. This is meters per second. This is meters cubed. But when we take a derivative, we're dividing by meters. So both of these end up with meters cubed per second. So if you like thinking about units, this violates no laws of units. So typically, how will we be using this? Typically in this class, we'll be using this where we have some flux integral we're interested in, and we're like, I don't want to do that. It turns out to be easier to do this. But often in physics, sometimes you might want to know this, and it turns out to be easier to do that. But the equality goes both ways. So let's practice using this. And I'm not sure we're going to do 3, but we should definitely get through 1 and 2, and then we'll see how we're doing for time. Through this? What do you think? OK. So here is doing, the divergence theorem says flux out of a closed surface is this total divergence in the surface. Total flux out is flux density contained in the surface. So we have 2 ways to do this. First, directly evaluating this, so we're going to work on the left-hand side. So we've got a cube, and this field is only flowing in the z direction. So nothing's flowing through the sides or the front and the back. So all of those are, I didn't write that, but you probably guessed, it's going to be 0. So we have to think about the top and the bottom. So it's centered at 1, 2, 3. So z is 3. And so then I need to go c halves in either direction so that this length is c. So then here in orange, 3 plus c over 2, 3 minus c over 2. And the outward direction on this surface is in the plus z direction. So that's why I have this here, dx dy. So I add up all in this direction. And then k is the direction, the outward normal. So k, oops, that's a vector, is just going to give me z squared. And then I realize, oh, but z squared is constant on the surface. It's just a plane. and it's constant at this value, 3 plus c over 2. So I just plug in 3 plus c over 2 for z, and happily, this does not depend on x or y. So we're integrating a constant, and we like integrating constants. It's just the area. The area in the xy direction is just c squared. OK, so then we have to do the bottom. And the bottom is different in two ways. One is that z is now at a lower altitude. This is the plane z equals 3 minus c over 2 instead of plus. But also, the outward direction has changed. It's now minus k. So the convention is we always orient surfaces, closed surfaces, so that outward is positive. So that's why we have, that's where this minus comes from. I seem determined to not put hats on unit vectors today. And then it's similar. I've got a minus out front. Z squared becomes 3 minus c over 2 squared. We're integrating a constant. We like integrating those. We have 4 zeros plus this. Adding them all together, everything cancels except for that.
Why did 6c cubed and not only 6c?
Because there's a c and a c cubed. Yeah. Oh, yeah. Sorry. Yep. So this is doing it, evaluating the flux interval directly. But now we have in our arsenal the divergence theorem, which says, we could also just calculate the divergence and figure out the total divergence contained inside the volume, and that will be equal to the total flux outside the volume. So we need to take a derivative, the divergence derivative, and it's going to just be 2z. Remember, the divergence is a scalar. It's a dot product, so it's no vectors anymore. So now we have a density, but instead of like butterfly density, it happens to be flux density. So we need to integrate 2z over this cube, dx, dy, dz. And I probably didn't need to write all of this, but again, x and y, or z is constant so far as x and y is concerned. So the first two integrals, we're just integrating a constant, and we like integrating those. That's going to give us c squared. Then we need to integrate 2z, and we're integrating over this volume, so z goes from here up to there. And if I do that and plug in, I get this, and at this point I say, aha, that is the exact same bit of algebra I had over there, which is not shocking because this is true. And then we end up with 6c cubed. So that's a nice application of the divergence theorem. So let's try the second problem. And this is similar, but we'll have to work around a cylinder. It looks like it's going to be gross, but it's not. So it should be maybe even a little less writing than this. So yeah, so give this a try, and we'll talk it through.